Hi everyone, myself Satendra Jaiswal and welcome to my channel Coding Card. So in our today's session, we are going to solve one graph problem. So you can see here the problem name is find the nearest clone. So I will be explaining you this problem in a very simple way. But before we proceed for this problem, I will request you to go and watch my previous video which was on shortest reach in a graph. So we have solved this problem where I have explained you this problem in a very simple way. And here we have used one concept, this distance list, how we were calculating the distance for each neighbor node, because this concept will be used in this problem along with some extra concept. So I will be explaining you, but I request you to go and watch that video first so that it will be helpful for you only and you will be more comfortable while solving this problem. So let me explain you this problem. So in this problem we will be given one undirected graph with n nodes where each node is a color. So we have to find the shortest path between two nodes of same color, and the distance between any two connecting node is of 1, means weight is 1. And if there is no any shortest path between any two node of same color, then we have to return -1. So for example, we are given a graph with node 5, 4 edges, and this is u and v value, and this is the color array, means each and every node are given with a color. So let me explain you here in a simple way first. So for example, suppose n equal to 5 means there will be 5 nodes. So node 1 connected to node 2, connected to node 3, 2 is also connected to node 4. Here we will give the color index in the right. And 3 is connected with node 5. And we will be given one array with color index. So color 1, 2, 3, 1 and 3. So for node 1, the color ID is 1. For node 2, the color ID is 2. For node 3, the color ID is 3. For node 4, the color ID is 1. And for node 5, the color ID is 3. So they will provide this ID for every node. Now, if you see here, for node 1 and node 4, we have same color. For node 3 and node 5, we have same color. And for node 2, we have different color. Now, they will ask, what is the minimum distance between two node of color 1? So what is the minimum distance? And they have also mentioned like the distance between any two connecting nodes, the edge is of weight 1. So the weight is here 1. So 1 plus 1, here will be plus 1 plus 1. So for color 1, the distance between two node of same color is how much? 1 plus 1, 2. And this is the path from here you have reached here. Simple. Now they will ask, give me the distance between two nodes whose color ID is 3. So node with color ID 3 is node 3 and node 5, and there is a single edge between these two nodes. So distance is how much? Only 1. So weight is 1, so distance will be 1. So this is also done. Now if they ask, give me the distance between two nodes whose color ID is 2. Whose color ID is 2. So whose color ID is 2. So for node with color ID 2, we have only one node which is 2 itself. So it will return -1. So this is the answer. If they ask, they will give in the problem statement, they will give the starting color ID from where we have to start. They will give. I will explain you for each and every color ID. So this is the problem and they have their explanation for the above example. Now let me go through the input format. So input format is very simple. In the very first line, they will have to integers value n and m, where n is the number of nodes and m is the number of edges. And the next line is about the m value, which is the number of edges, and these value are u and v, starting to the ending, means from which node to which node, the connection value. And next line is the color id array, and the last line contains the id of the color to analyze, like they will give the color id from where we have to start. So let me explain you this sample input one by one, then we will start with our concept how to solve this problem. So let me take the first example. So they have given node 1 with color id 1, node 2 with color id 2, node 4 with color id 1, and again node 3 with color id 1. So if you see here we have three nodes, node 1, node 3 and node 4 with same color id, which is 1. And in the problem statement also they have given the start id of the color is 1. So if you see here, what is the minimum distance between two nodes of the color id 1? So there is one path which is, so there is one path, this one, these two nodes are connected with same color id 1, and one path is this one. So one is between node 1 and 3, which is of distance 1, and one is from 1 to 2 to 4. So here we have distance of length 2, edge 1 plus 1, right? 2. But we have to return the minimum distance. So we have to return this one as an answer. So the path will be from 1 to 3. So this is the first example where they have given 4 nodes and the color ID for all the 4 nodes, in which for node 1, 3 and 4 the color ID is 1, and for node 2 the color ID is 2, and start ID is of color 1. So this is the example where we have found the minimum distance is 1 between node 1 and 3. This was the very first example. So this was the example where they have given the node and the color ID, and the start ID is 1. So here they have written the output as 1. Now let us go for the second example, 1, 2, 3 and 4. So next example is node 1 connected to node 2 connected to 4, and one is connected to 3, and they have the color id 1. For node 2 the color id is 2, for node 4 the color id is 4, and node 3 the color id is 3, and they have given the start id as 2. So you can see here we have only one node with color id 2. So by default here for color id 2 the distance will be -1, because we have only one node which is node 2 with color id 2. So we cannot reach to any other node. So here the answer will be -1. So they have given here. So they have given here -1. Now next is this one. This is an interesting one. Now next one is node 1. Node 1 is connected to node 2, connected to node 3, 2 is connected to 4, and 3 is connected to 5. And they have their color. 1 is having ID 1, 2 is having 2, 3 is having 3, 4 is having 3, and 5 is having 2. So here we have node 2 and node 5 is of same color, and node 3 and node 4 is of same color, and node 1 is of different color. And the problem, and in the problem statement the start id is 2. So for id 2 we have node 2 and node 5 with the same color id 2. So distance will be how much? So if you see here, the distance will be to reach, if you are starting from node 2 to reach node 5, the distance will be plus 1, plus 1 and plus 1 to reach here. This is the path to reach. So for color ID 2, the distance will be 3. So 3 is the answer. You see here. So the output is 3. So with the help of visualization, it is very simple to find the output, right? But how to write the logic? That is the main task. So how to solve this problem? So that's why I said before solving this problem, go and watch this video where I have explained this distance logic, distance list logic, how to keep the distance of each neighbor. So we will be using the same logic over here. So we will be using the same logic here. We will be having one distance list, and here we will be adding one extra concept, which is the source list, in which we will keep the track for each and every neighbor, how we have reached to that neighbor, what was the source. So, and we will be using simple BFS traversal, and the concept is like, let us take this graph as example, and I will explain the concept here. We have a node 1, node 2, node 3, node 4, and node 5. All right, and we have this target node, node 2 and node 5. Okay, so let me write here first. Let me write here the nodes. Nodes are node 1, 2, 3, 4, and 5. Okay, and the target node is what? Node 2 and 5. So for example, here in this graph, the color ID 2 are having node 2 and node 5. So in earlier BFS traversal, what we were doing, we were only keeping the node start source node in the queue. But this time what we will do, we will keep all the target node of same color in the queue. So here the target color is node 2 and node 5. So we will keep this node 2 and node 5 in my queue data structure for BFS towers. And what we will do, we will do our BFS traversal one by one, starting from this 2 node first. And the same logic, we will simply pop this node and apply our BFS traversal logic with some add-ons over there, and we will add its neighbor in the queue at the end. So we'll apply that same logic with some add-ons. Now let me explain you here. Now what we will do, we'll keep on distance list. So if we are starting from node 2 and node 5, so the distance for node 2 and node 5 will be 0 by default, because we have kept this node 2 and node 5 in our queue data structure 2 and 5. So we will be starting from node 2 and 5. So for these two nodes, the starting distance will be what? 0. So this in the distance list for these two nodes, the starting value is 0. And for the rest, we'll keep by default minus 1, and minus 1. Make sense? Now here we'll be using one extra concept, which is source list. Okay. So source list is what? Suppose we are standing on any node. For example, suppose this is node 1, this is node 2. These both are connected. Now if I'm standing here, currently I'm standing at node 1, and if I'm going to node 2 here, node 2, so what will be the source for this node 2? How I have reached to this node 2? What is my source? The source is node 1. So for every neighbor, we will be traversing and we will be updating its source, from which source we have reached to that neighbor. So this is one extra concept here. So suppose if we are starting with node 2 and node 5, node 2 and node 5, node 2 and node 5, node 2 and node 5. So what will be my source for node 2? The node itself, and for 5, node 5. Because if I am standing at node 1, then source for node 1 will be what? the node itself. So if we are starting for node 2 and node 5, so for them the source will be the node itself, and for the rest what we will do, let us keep default value -1, -1, -1 and -1. All right. So now let me explain you the concept in detail here. So we have this. Let me explain you again. So I have made this neat and clean initialization, and we had one queue data structure in which we have node 2 and node 5. Now they have given that 2 is the start ID. So what we will do, we will simply pop left, right? So when we pop left, so 2 will be popped out. Okay, so 2 will be popped out. So what we have to do, we have to play with its neighbor, right? So its neighbor are node 1 and node 4, right? So from this queue, node 2 is popped out. All right, so we have to apply our logic here. So for node 2, we have already updated here. For node 2, the distance will be 0. For this node 2, the distance will be 0, and the source for this node 2 is the node itself, right? So for this we are clear. Now its neighbor is node 1 and node 4. So for 1, again its distance will be how much? We have only one edge connecting node 2 and node 1, and its distance is 1. Now we are standing at node 2 and its neighbor are 1 and 4. So how to calculate the distance? So distance of neighbor will be how much? The same concept, distance of current plus 1. 1 is the edge weight. So distance of current is what? Here distance you can go and see in the distance list. So distance of current is what? 0 and plus 1, and this neighbor value is node 1. So for 1 we will be updating its distance as 1, right? So distance list will be updated with value. For node 1 it will be 1, for 0 it was 0, for 3 it is -1, for 4 it is -1, and for 5 it is 0, right? And source, and the source, how we were able to reach node 1? The source will be what? What was its source node? Node is 2. So for node 1 we will update its source as 2. So for node 1 we updated its source as 2. Let me update this source list. So for node 1 we have reached with the help of node 2. Node 2 its source is by default node 2. For 3 it is -1, for 4 it is -1, and for node 5 it is 5 itself. All right. Now one node is clear. Next is node 4. So again for node 4, again the distance will be what? Distance of current plus 1. So currently we are standing here. Distance of current is how much? 0. If you see here in the distance list, for node 1, 2, 3, 4 and 5, right? Let me highlight this one. This was the node, right? And if you see this way, it will be easy for you. Now see, so for 4, what will be the distance? Distance of current plus 1. So current is what? Node 2. Node 2 is having distance 0 plus 1. So which will be 1. So for node 4, the distance will be 1. So this value will be updated with 1. Making sense? Let me write properly. Node 1, 2, 3, 4 and 5. Distance where for node 1 the distance calculated is 1. For node 2 it was 0. For node 3 the distance was -1 by default. For node 4 we calculated the distance as 1, and for node 5 the distance is 0. And the source list, to reach node 1 the source was node 2, for 2 it was node itself, for 3 minus 1. To reach node 4, here, reach node 4 the source node was node 2, and for 5 it is the same, node 5 itself, right? So till here we are done, and our graph was, let me again take this graph, 1 2 3 4 5, 1 2 3 4 and 5, and this was our required things, right? Now we are done. This node is also visited, this node is also visited, and our q was having value 5 because 2 was already popped out. And what we will do, we will add its node 2 neighbor 1 and 4 in the queue. I hope till here we are okay. Now next is node 5 to be popped out. So when we are popping 5, so for 5 the node neighbor is 3. So we are currently standing at node 5 and its neighbor is node 3. So the distance for node 3 will be how much? Distance for node 3 will be how much? Distance of current plus 1. So for node 5 the distance is how much? Go and see in the distance list. 0 plus 1. So it will be 1. So for 3 the distance will be, this is distance of neighbor. So distance will be 1. So let me update this one. So distance for node 3 will be 1. And its source will be how we were able to reach node 3. From which source? That source is node 5. So this will be updated with 5. Okay. So 3 is also visited, right? And what we will do, we will in the queue we will update 1, 4 will be there, and for 5 its neighbor was 3. So 3 will be added in the queue. Now 1 will be popped out. Right? Now its neighbor are 2 and 3. Alright. So in our all previous problems, what we were doing, if the node neighbor is already visited, we were going to the another node, right? To the another neighbors. But here we have a catch. What we will do, we are currently standing on node 1. Okay. Currently node 2 and node 3 are its neighbor. 2 and 3 both are visited. So this is the main concept. If we are standing on any current node and its neighbor is already visited, so in else part we are going to check whether that visited node is cause of the same source. Like if this 2 was visited cause of the same source. Currently I am standing on node 1 and here my source was x. Cause of x I reached to node 1 and my neighbor node is 2, and this 2 was visited. But if this 2 was also visited cause of the same source, then we are okay, nothing to do. So if you see here, for neighbor 1 the node is 2. Okay, this is visited. It will go in else part and check the source for these two, node 1 and node 2. So for node 1 and node 2, both the source are same. Okay, no issue. Let's move forward. If both the source are same, means that is already traversed with the same node. Now it will go for the next. Now it will go for the next neighbor. So here I am standing at node 1 and my neighbor is node 3. Okay, node 3 is also visited, but it will check. For node 1, I am standing at node 1. What is my source? My source is node 2. And for 3, what is my source? Source is 5. Here the source of node 1 is not equal to source of node 3. You can see here the source is 2 and here source is 5. Means this is the catch. If the nodes are visited but the source are different, it means previously we have started a BFS traversal for node 2 and node 5 and the nodes were listed in a visited. Okay, so this 3 was also in a visited, node 1 was also visited, but this node 1 was with the same source with a 2, and here node 5 was, here node 3 and node 5 was with the source node 5. All right, currently we have reached at a stage where we are standing at node 1 and its neighbor for node 2 is correct because the sources are same, so nothing to worry. But for neighbor node 3, the source is different. It means the node is visited but source is different, means previously there is a BFS traversal which have traversed to this node. So here is the catch. Let me explain you again. Node 1, node 2, node 3, node 4 and node 5. So this was the graph and node 2 and node 5 were of same color, right? And we know the source for node 2 is the node itself. The source for node 4 is the source 2 because we are reaching with the help of node 2, and source for node 1 was also 2, right? And source for 5 was 5 and source for 3 was 5, right? You can see here. So you can see here the source list which I have already explained. So currently we are at node 1. So currently we are at node 1 and the situation is like it has its neighbor 2 which is already visited, and we have node 3. So 2 and 3 both are already visited. So it will go in another condition where it will check if I am standing at node 1 and its neighbor is 2 and neighbor is 3. I am standing at node 1. I am checking for the next neighbor which is 2. Okay, this is visited, no issue. Whether its source is same? Yes, the source for this node is same. So nothing will happen here because it is a part of same traversal, same BFS traversal. Now for node 1 and node 3. So here the source was 2, but here the source is 5. So in this situation, let me erase this one. In this situation where the source are different, it means this 3 was being already traversed, means part was already traversed with some different BFS traversal. Like initially we have kept node 2 and node 5 in our queue, right? Initially, because node 2 and node 5 were of same color. So we kept this node 2 and node 5 in the queue, right? So this 3 was a part of node 5 BFS traversal. So till here part has been already covered, means this is required, right? Means we are reaching to a path where we met with an intersection. So we have reached to the situation where this is the intersecting point of the two traversal. One was starting from node 2 and which was going in this direction, and one was starting from 5 and going to this direction, and we have reached at a situation where this is the intersection point where the sources are different, right? So in this situation what we have to do, we have to write the logic. So distance will be how much? Distance of the current plus distance of the neighbor, distance of the current node on which you are standing, plus distance of this neighbor, right? We don't know what is the value because this value is already been calculated. So what we will do, distance of the current node on which we are standing plus distance of the neighbor, like For 3, it has been already calculated when we have started the BFS traversal with node 5. So it will add 2, and we know for this connecting there will be a weightage 1. So 1. So the distance will be distance of current plus distance of neighbor. So this will be the formula. Let me write properly. So this is the situation when source of current is not equal to source of neighbor, right? This is the condition when source of current is not equal to source of neighbor. The nodes are visited, but their source are different. Means they are the part of two different traversal and meeting at an intersection point. So what we'll do, we'll calculate the current distance on the node which we are standing plus distance of the neighbor node, which will be the part of any previous BFS traversal. So that distance plus the weight 1, the distance between those two connecting nodes. So this will give the total value. So if I calculate here, my distance will be how much? Distance of 1 plus d of 3 plus 1. So go in the distance list. So d of 1 is 1, d of 3 is 1 and plus 1. So 1 plus 1 plus 1. 1 plus 1 plus 1. So we got the total 3. So this is the answer. So this was the main concept here. Like earlier we were doing the BFS traversal. If any neighbor node was visited, we were simply going to the next neighbor. But here we have to go in else condition and check if their source is different. If their source is different, then we have to simply add this logic. Add the distance of the current plus distance of the neighbor plus 1. The distance between these two nodes, current and its neighbor. Simply. That's the logic. So let me explain you one more time in a very simple way. Like in this graph, 1, 2, 3, 4, and 5. So we started from node 2 and node 5. BFS traversal. BFS traversal cause in the queue we have kept 2 and 5, right? So with the help of 2 we have reached, we reached node 1 and node 4. So 1 and 4 were being traversed in this manner, right? And this 2 was popped out and its neighbor 1 and 4 was kept, right? 5, 1 and 4 was kept. 2 was being popped out. Now we popped out, now we popped out 5. We popped out 5. So with BFS of 5, now for 5, we started the BFS from here and reached to its neighbor 3, right? And the source for 5 was 5. Here the source was 5, but here the source were 2, 2 and 2. All right. And after 5, we kept its neighbor 3 in the queue, right? So a situation came when 1 was popped out, right? When 1 was popped out, situation came when 1 was popped out. 1 was popped out. So its neighbor were 2 and 3. And both 2 and 3 were already visited, right? So we were checking in else part whether their source is different or not. So for node 1 and node 2, the source were 2. So we were okay. Like this is the part of same BFS traversal. So nothing to do. But for 1 and 3, here the source was 2, but here the source was 5. Here the source were different. So this 3 was the intersection point for two BFS traversal. One was coming this way and another was going this way. And this was the desired path, right? So we came with a formula. So in this situation where the neighbor nodes were already visited, so we came with a formula to check its source. If the source are different, then the distance will be distance of current on which we are standing plus distance of its neighbor, distance of the neighbor node which was already traversed as a part of some different node DFS traversal, and plus one extra the distance between those edges, right? So we came with this formula and we'll simply return this one. So I hope you understood this explanation. So we'll apply the same logic in the code. So let me write the code here. So we have to write the code, find the shortest where they are passing the graph nodes u, v, IDs and the starting ID. So we have to write our logic here. So let me zoom out. So the very first step is to build the graph. So they have given the graph nodes. So what we will do, we'll take a graph. So we'll take a graph and initialize first. So for I range, in range from 1 to graph of nodes plus 1 from 1 to n. All right, and we have to initialize as a dictionary type where we will be keeping all the I value as a key and the empty list as a value. So we have initialized the graph. Now here we have initialized the empty graph. Now next thing is to initialize u and v value. So for u comma v in graph, not graph here, because if you see here in the problem here, they are passing from and to in a separate list. So what we will do, so here in this problem they are passing from and to in a separate list, but we need u and v as a tuple like this, right? So what we will do is simply apply a zip function here. So it will keep the value one by one, like 1 2 3 it was in the list from, and 5 6 was in 2. If we apply zip function here, so if we apply a zip function here, so 1 and 5 will be as a unv, 2 and 6 will be as unv, and 3 and 7 will be as unv. So we'll simply apply a zip function over here. So for u comma v in, simply zip function for graph from comma graph to. So it will give us u and v value. So this is one extra thing we have to do, and a simple logic like the same thing, graph of u dot append v, and for v we have to append u, graph of v dot append u, right? Simple graph initialization. So only one thing, we have to use the zip function over here to get u and v value from two separate lists, right? So we are done till here. So this was step 1, right? Next step is to find the next step is to identify the nodes with the target color. Okay, so they have given the IDs. Now we have to find the total number of IDs of same color. Okay, so for that we simply write a condition target underscore nodes equal to, we simply apply a for loop, target nodes equal to, so we have ID list and the value. We will simply compare every list IDs with the value. If they are matching, we will simply add in the target nodes. So simple logic for I in range from 1 to g of nodes 1 to g of nodes plus 1. Okay, and what we are going to check, if id of its IDs id I minus 1 equal to equal to val means we have to keep that I value, right? So we are simply identifying the total number of target nodes so that we will keep this in the queue, all those target nodes in the queue for our BFS traversal. Now, don't get confused with the ID -1 cause let me explain here. They are giving the IDs as a list. They will give IDs like 1, 2, 3, 1, 3. So this is ID, but its index is 0, 1, 2, 3, 4, right? So your index is starting from 0, so don't get confused. That's why I've written ID of I -1. So this value will be starting from 1. Our loop is starting from 1, so ID of 0. ID of 0 is having value, some value, right? So that will match with the color value here. So we are simply targeting those as a target nodes. Now we are done. We will simply write a if condition. If the target node's length is less than 2, the target node if the target node length, like if there is single target node, no need to proceed with the BFS traversal because there won't be any matching node of the same color, right? So if the length of the target node is less than 2, what we have to do? We have to simply return -1. We have to simply return -1 as answer, right? No need to do any BFS traversal. Now, till here we are okay. Now we will apply the concept here. Now we will apply the concept here. Let us take one queue data structure. Q equal to dq, and let us import this from collections import du, right? So q equal to dq, empty dq. Now here we have to take two lists. One was the distance, distance list, and one was the source list, right? Now what we will do, we will initialize this distance list with -1 for all the nodes. So graph of nodes plus 1, right? Graph of nodes plus 1, and same for the source, right? Source equal to -1 with the graph of nodes plus 1 till the total number of nodes we are initializing with -1. Now what we will do, so this is for distance from the start node, and this is for source node of the same color. Okay, we are done. This was the initialization part. Now what we will do, initially in our previous BFS traversal we were adding only the source node to the queue, but here what we will do, we will add all the targets node in the queue for node in target nodes. What we will do, queue dot append node, and whenever we are appending the node in the source, in the distance list, the distance of node for the node which we are appending, it will be 0, because if you are standing on any node to start with, its distance will be 0 and its source will be the node itself. So source list will be updated with source of node will be the node itself, correct? Like if you are starting with node 2, so its distance will be what, 0, and its source will be the node itself. So we initialize this value. So we are done with the initialization. Means, for example, there are 100 nodes, out of which 10 are of same color. So what we did, we appended all those 10 in the queue for the BFS traversal one by one, and in the distance list for each node, the distance will be what? 0. Like for all those 10 nodes will be the starting point for each of them, so their distance will be 0, and their source will be what? The node itself, because they will be starting from itself, right? So the source will be the node itself. So we are done. Now we'll apply the BFS logic. So while while q while q, what we are going to do? Q dot pop left, and we will be saving this in current equal to q dot pop. Now we pop the leftmost element from the queue. Now what we will do? We will traverse the neighbor for this current element. So for neighbor in graph of current, the same logic for the BFS towers, the same logic as the BFS traversal. What we will do? Now what we will do, we'll simply check if distance of this neighbor, if the distance of this neighbor is equal to -1, means that node is not visited yet. What we will do, we will simply update the distance. So distance distance of this neighbor will be what? Neighbor equal to distance of the current node on which we are standing plus 1, which is the distance between any two connected node, which is 1. By default they have given. So this is done, and at the same time we will update the source for this neighbor. So source of this neighbor will be what? Source for this neighbor will be what? And source for this neighbor will be what? The source of the current node on which we are standing, right? The same logic which I have explained to you, we are implementing in the code. We updated the distance for the neighbor equal to distance of current plus 1, and the source for this neighbor node will be what? The same source of the current node on which we are standing. After that, what we will do? Q dot append its neighbor, right? Simple BFS logic. Till here we are done, no issue. Till here all the logic were similar, right? Only we have added this extra logic for finding the source node. Okay, now after this if condition, if the node is already visited, we had one more logic where if the nodes are already visited, we were checking if the source for this if the source for this neighbor, if the nodes are already visited, then we were checking the source value, if the source are equal or not. If the source are not equal, if source of neighbor not equal to source of current, then we have applied the logic to find the distance d equal to distance of current plus distance of neighbor plus 1. The distance between those two nodes, okay, plus 1. So this was the logic if the nodes were not visited. So we simply calculated the distance, updated the source, and added the neighbor in the queue. So here, if the nodes are not visited, we came with this logic. Now, if the nodes are visited, then we have to come with some different logic. So we came here, we were checking the source. If their source are different, we came with this logic, right? I explained you why we came with this logic. And instead of saving this in a D, we will simply return from here. Calculate the distance of the current plus distance of the neighbor plus 1. And at the end, if no any condition is satisfied, we will simply return -1. We will simply return -1. Simply return -1. So this is the logic. So let us run this code. So we are getting one indentation error for line 35. So you can see here it is passing. Now let us submit this code. So you can see here all the test cases got passed. So the problem was very interesting where we have to apply one logic for the source list in which we were tracking the source node for each and every neighbor and current. And this was the main logic here. So I hope you understood this problem in a very simple way. So this was the catch here. So if you have any different solution, do post in the comment section. I will review from my end and that will be helpful for others as well. So if you have learned something new, please give a thumbs up and subscribe to my channel Coding Card and stay tuned for the next videos. Thanks for watching.